All right, folks, welcome. Today we're going to talk about the 60 to 1 rule as it pertains to instrument flying. The 60 to 1 rule simply says this. I'm going to break it down into a very simplistic formula in a way that you can actually use it in real time, and you can throw it in your flight bag, the little formula, or have it pre-programmed in a calculator, or just do the math in your head too as well. You can do it that way. And it's used in the world of instruments for various different things. And if we've flown together, if I've had the chance to instruct you, or vice versa, you know that I break things down in very simplistic, easy to understand terms, because that's the only way I can get my mind around it. So what we're going to talk about is the 60 to 1 rule, 60 to 1 rule, sometimes written like that. Sometimes you could write it out. 60 to 1 rule. And all it says is if I have a VOR or VORTAC or some other station with radials coming out of them, of course I'm going to draw this a little bit exaggerated. If I have 1 degree of radial, then at 60 nautical miles I have one nautical mile of arc length. And I say that because it's actually the segment of an arc here. In fact, it's a 1 degree or 1/360th, because there's 360 degree circles. Here there's 60 degrees in a circle. This arc length here is 1/360th of an entire circle. So in other words, all we're doing is taking the entire circumference of a circle whose radius is 60 nautical miles, and we're taking 1/360th of that, and that's what we're calling this distance. Now in the world of flying, nobody cares about arc distance. We care about straight line distance. And it just turns out these two at 60 nautical miles are very, very close to one another. In fact, you can kind of derive it yourself. Just knowing the circumference of a circle in basic geometry is 2 pi r, pi being 3.1416. So if we take something around there, I think that's what it is, times 60, because we're talking about a 60 nautical mile radius. This number here is the circumference of a circle whose radius is 60 nautical miles in diameter. And since we're talking about one little sliver of this circle, in other words, 1 degree, which is 1/360th of this circumference, we can take this whole number and divide by 360. And you know what number we get? We get 1.04 nautical miles. Rounded up, of course. What that means, and 1.04 in everyone's mind, to include mine, is 1 mile. So back to our original diagram, what that means is if I have a VORTAC or a VOR or some other station here that transmits radials, here's 1 degree. Our straight line distance is about 1 nautical mile. And by the way, if arc distance is 1.04, odds are straight line distance is very, very, very close to 1 nautical mile. And of course, that's out to 60 nautical miles. And so there's a ratio. When we say 60 to 1, that's a ratio. We could also do it in terms of a fraction, or we could write it out in English, right? We say miles per gallon, that's a ratio. If you get 25 miles to the gallon, there's a ratio. If you make, $3,500 per month, that's a ratio. It's the same thing here. That's all we're doing is talking about ratios. And ratios also establish relationships, and they also establish rate of change. In other words, for example, in this, I just erased it, but I'm going to redraw it. If 1 degree at 60 nautical miles is 1 nautical mile, then as this radius goes up, then this nautical mile no longer becomes a nautical mile anymore. It increases as the radius goes up. There's a relationship between radius and arc length right here, or what we could call offset between radials. So as the radius goes up, the offset goes up. As radius goes down, offset goes down. Same thing with the degrees here. If 1 degree at 60 nautical miles is 1 nautical mile, then a half degree at 60 nautical miles is half a nautical mile. And so that's all that is a relationship between these three things. And bottom line, you can take that relationship and play around with the numbers a little bit and discover that the arc distance which is this right here. If you can see that. Here's our station. Here's 60 nautical miles if we were to draw the 61 rule. And instead of just putting, because we're not always going to be at 60 nautical miles, so instead let's just call that distance, or distance from the station, distance from our VOR, VORTAC, or whatever nav aid we're using. And let's call this offset. We could call it arc distance if we were talking about geometry, but the reason why we work this problem out in the world of instruments is I want to know if I am here and I want to be here, what's my offset from the desired radial? So we're going to use term offset over there. So that's distance, that's offset, and then of course this could be just degrees right there. So we'll find out if we play around with the numbers a little bit that the relationship between all this looks something like this. So here we go. Our offset is equal to the number of degrees we're talking about times our distance divided by 60. That's it. Divided by 60. And there's other ways too, and we're going to talk about those without using this formula necessarily. We'll do that here in a little bit to calculate numbers using the 60-to-1 rule. But that's basically what you're looking at right there. So let's come up with a couple of examples. Okay. So the question is, we are 2 degrees off of course. Let's just learn to spell here. 2 degrees off of course, and we are at 50 nautical miles. What is our offset? How many nautical miles off that track are we? So pictorially, it would look something like this. Here we are, flying inbound or outbound to the station. It doesn't matter. Okay. There's 2 degrees from the radial that we're on to the radial that we want to be on. And we are currently at a distance of 50 nautical miles. The question is, how far laterally, or straight line distance, are we? In other words, what's our offset? Well, plugging in the numbers into our formula here, our offset is equal to 2 degrees times the distance. I started right distance, but we already know that. 50 nautical miles divided by 60, which is 2 times 5/6, which is 10/6, and 1/6 would be what? Well, 1/3 is 0.33, 1/6 is about 1.7 times 10. I'm not even going to try to do that math. 1.7-ish or something like that. In fact, you'd think that I would be, well, my calculator's on my phone. My phone's what I'm using to print this, or record this. So in other words, our offset is 10/6 of a nautical mile. Well, we know 6/6 is 1 mile, so if we take that out, that leaves 1 mile and what? 4/6 left, and that obviously comes out to 2/3. So 1 2/3 mile. That is this distance. Or 2/3, you can call it 0.67, sorry. So we are 1.67 nautical miles off our desired course. That's how we would use that formula. Let's come up with another one. I'm going to erase this whole thing. I'll write the formula up at the top. Our offset, you could use whatever term, whatever works for you. Our offset is equal to the number of degrees we're talking about in question times the distance in question divided by 60. So here's another example. We are 120 miles away from the station. Okay. We are 5 nautical miles off course, off the desired radial. The question now is, how many degrees is that? Well, again, back to our formula, just plug in the numbers. We're 5 nautical miles off course, so our offset's 5 nautical miles. We want to know the degrees. We just said that, how many degrees. We said that we're a distance of 120, and of course we fill in the constant here of 60. If we do that math, we have 5 equal degrees times 2. We do the math here, and all we got to do is divide both by 2, and now we get 5 divided by 2 equals degrees, and 2, that's 2.5. So we are 2.5 degrees off course. 2.5 degrees off course. Let's do another quick one. And then we'll ask ourselves, hey, in the cockpit, how would I actually apply this more realistically than having dry erase board and a whiteboard marker here? Let's come up with one more. Let's say that we are 3.5 degrees off course, off our desired radial, and we're 25 nautical miles. In the world of GA, this seems more appropriate than being out there at 120 nautical miles. So 3.5 degrees off course, we're 25 nautical miles from the station. How many miles off course are we? In other words, what's our offset? What's our lateral distance here off our desired course? Well, again, let's plug in the formula. Offset equals degrees times distance or range, whatever term you want to use, divided by 60. Now all we got to do is plug in the values. We're looking for offset equals 3.5 degrees, 3.5. We're a distance of 25 divided by 60. I'm not even going to attempt to do that math. I should have preserved a calculator. In fact, I think I have. Yep, actually I do. Stand by. So if we do this math, 25 divided by 60 times 3.5, 25 divided by 60 equals times 3.5. We are 1.45 or 1.5, if you want to round it up, nautical miles off course. There you have it. Okay? Let's do another problem that'd be a little more realistic in the cockpit, although that question is actually very realistic. What kind of stuff am I going to have in the cockpit to show me, excuse me, the degrees off? Well, I have a VOR nav aid, right? What we call an OSB. By the way, this knob here is called an OSB, but the instrument itself too is called an OSB. Many of them have a donut in the middle, and then we've got dots after that. If you have a donut, one edge of the donut is considered one dot. So as we know, every dot equals 2 degrees. I guess that's a poor way to write 2 degrees. Every dot's 2 degrees on these instruments, okay? So suppose I have something that looks like this. Okay, well here's the center. That's 1 dot, 2 dots. I am 2 dots off. We know that every dot is 2 degrees, so 2 times 2 equals 4. I am 4 degrees off of my desired course. 4 degrees off my desired course. My range is 30 nautical miles for my VOR, so let's figure out how many miles laterally am I off of course here. Well, again, plugging in our formula, let's just write it first of all. Offset equals degrees times, our distance or our range divided by 60. And all we got to do is figure this out. Offset equals 4 degrees. We said we were 4 degrees off. Our distance is 30 divided by 60, which is a half. 4 times a half, which is half of 4, is 2. Therefore, our offset is 2 nautical miles. 2 nautical miles. That's it. That's it. That's how you would use this during navigation. You're trying to figure out, or maybe you're asked, I don't know, how far off course are you, or you just kind of want to know what the winds are doing to you. That's one application of the 60-to-1 rule. And what I want to do now is describe to you the concept of how we would use the 60-to-1 rule to calculate a lead radial. Now, a lead radial is something that looks many times like this. Here's my localizer signal to the inbound runway, and we have an arc. and we arc, and at some point here, before we actually get centered up on the localizer signal, we have to start our turn inbound. And it's always published on the approach for us, and it'll say LR for lead radial, and then of course it'll give us 1, and it'll say 0, 0, 1, 0. The question is this. Does that lead radial work for us? Because there's some assumptions when the people that built the approach, and they're typically terpsters, terminal en route procedures people, when terpsters build these things, they have certain assumptions about turn rate, turn radius, etc., which is driven by bank angle G's or true airspeed. The point is, this lead radial calculated for you and I may not work for us. So here we are flying along, we hit that lead radial and start our turn in and find out it's way too early. Or we got to end up just doing this 2-degree bank angle turn when we could have just waited and turned here and done a standard rate turn to intercept. Or maybe we're a fast mover and we start our turn at the published lead radial and end up flying well past this thing. So here's another great example of how we could use the concept of 60-to-1 to calculate a valid lead radial for us. Now, I'm not going to bore you in this video because I want to focus on 60-to-1 rule in this video, but you could go out there and just very easily Google what determines our turn radius, turn T sub rad if you want. And it's a function of bank angle G and also true airspeed. So you can figure on any given day, yes, it's going to change based off temperature and the altitude, the PA, the pressure altitude during that time at which I'm shooting approach, and it's going to vary from approach to approach to approach, location. But generally speaking, you're going to have a fairly constant true airspeed as you fly. And we know this to be true because that's why 9 times out of 10, you'll fall in the same category of approach, category A, B, C, D, and on down to E, for your particular airplane. So you're going to come up with a certain turn radius. And there's R, turn radius. And we have that fixed turn radius, and you calculate that yourself, whatever that is. But it's a given distance. It's a given distance. So what that means is if I have an inbound course, either a radial or maybe even a localizer or something like that, then and we have to calculate a lead radial, we have to ask ourselves, what radial do I use? Let me draw that a little better. What lead radial do I use? So in the world of general aviation, it's not too far to imagine that our turn radius could be about a half a mile. Or you could say 3,000 feet if you want to, which is about half of a nautical mile. But let's call it half a mile. So if we're arcing, and I want to start my turn a half mile prior, so in theory I line up perfectly on the inbound radial, the inbound course. And by the way, all of this assumes that the station or the VOR you're using for these radials is co-located with the airfield that the ILS is on. Very, very close. Or of course, if you're shooting a VOR approach, you would never change nav aids. But this assumes that your nav aid is co-located with the airfield that you're arcing to, or where the approach is on. You know what I'm trying to say. But let's assume then that this distance here, from here to here, is 1/2 nautical mile. And let's come up with an arc distance. Let's say we're going to do a 15 DME arc. I'm going to draw the big D here. 15 DME arc, and I've seen some down to 9. I've seen some out to 20, 23, 27. It all depends where the station is. So the question is then, because I don't have anything, of course, some systems will show you this cross-track distance, but we're going to go old school and assume that all we have is an OBS or VOR instrument, whatever you want to call it. And I'm going to dial in the top here what my desired lead radial is, and when my CDI centers up, we're going to start our turn inbound. The question is, if this is, for example, 180 inbound, what radial am I going to set up to lead my turn inbound 180 on my inbound course? Well, it's kind of similar. Take that formula again. Offset equals degrees times distance divided by 60. It's the same thing. So if our offset is a half mile, because our turn radius is half mile, so we're offsetting a half mile, degree, our distance is 15 divided by 60. Half equals degree times 1/4. 15 goes into 15 once, 15 goes into 60 4 times. But remember, we're looking for degrees here, right? We're looking for degrees. Now I'm going to do a little bit of kind of algebra here. So remember this. So let me rewrite that over on this side. 1/2 equals degree times 1/4. Okay, you guys with me? So we're going to do a little bit of basic algebra over here. Right there. So here we go. 1/2 equals degree over 4. That's what that is. Well, obviously, we're looking for degree. That's the unknown. And to get rid of this 4, we're going to multiply both sides of the equal sign. So we end up with 4 over 2 equals, these cancel out, degree. And of course, 4 divided by 2 is 2. 2 degrees. There you have it. There you have it. So if our inbound localizer or our inbound radial for VOR approach is 180 inbound, the reciprocal of that is 360. That means we want to dial in up at the top here 2 degrees prior to that. That means our lead radial is going to be 002. And I will dial that up here. And of course, while we're flying, that CDI is going to be over here. And then as we're arcing closer and closer and closer, as soon as, and this thing will start swinging down, and as soon as it centers up inside the donut, we start our turn inbound using whatever parameters I used or assumed to calculate a 1/2 nautical mile turn radius. Given true airspeed, given bank angle, given turn rate, G's being pulled, whatever assumptions I use, I execute them there. And of course, while I'm in the turn, none of this matters anymore. So what do I dial in? 180. And by the way, this should be pretty darn close, already centered up for us. But this is an example how we can use the 60-to-1 rule to calculate a lead radial as we're coming from the arc, as we're arcing to a course or arcing to a final. And that's an arc. And the mathematics is almost identical if we weren't arcing, right? If we were just on some, I don't know, for some reason, maybe we're Nordo, no radio, and we're having to calculate or do our own navigation to an inbound course. There's some radial here that I'd want to hit. In other words, not really radial, distance is what I want. So some track distance that I would want to turn 45 degrees and put ourselves on kind of a self-made radar down dog leg, because we never want to hit our, especially a localizer, they're so sensitive, or an LNAV inbound course, right? LNAV, LNAV VNAV, or LPV, or LNAV with plus V, all these other things. We don't want to just go blitzing through this at 90 degrees. So somewhere in here, we'd want to turn a dog leg so that the CDI comes across very slowly and very controlled, and we can do that right here. So we could calculate a lead radial that gives us the same mechanics, the same outcome as a normal lead radial if we're arcing to final. So that's our 60-to-1. That's our 60-to-1 rule and how we can apply it in our planning and or flying. And again, all it says is at 60 nautical miles, there's one arc nautical mile distance, 1.04 arc distance or straight line distance of about 1 nautical mile at 1 degree. And if we play around with the numbers and you can derive this formula, that means our offset from any given course is equal to, in other words, offset in terms of nautical miles is equal to the number of degrees we're off course times our range or distance from the nav aid divided by 60. That's the formula to remember. Now, look, I've seen other formulas that are similar to this in other subject areas in the world of science and mathematics, and I've looked at it and I've had to derive my own. You could easily come up with something here. You could say this is offset equals degree divided by 60 times the distance. You could use basic algebra to arrange this any way you want. You could say offset right here divided by distance equals degrees divided by 60. So you can play around with this to make it look like something or match something that you can memorize better or make better use of. But that is your 60-to-1 rule, how you'd use it during navigation en route or departing an airfield, and how we could use it as we're arcing to final. In other words, use it to calculate a lead radial so we know when to start our turn inbound to final. Well, folks, I hope that helped. I hope you find it useful. If not, let me know. And whatever comments and suggestions, etc., you have, if you watch my other videos, whether they're related to astrophotography, science, astronomy, physics, or aviation, I love hearing feedback. I love hearing from you. And certainly if there's a mistake I've made here, dear Lord, please tell me. And if you've even remotely liked this explanation and what we've talked about here, then you would love my instrument pilot study flashcards. I am a fan of flashcards. One card, one question, one answer on the back. That's it. I have to study that way. You can't hand me a card that's got 8 questions with 8 answers. Because what if I know one of those answers? What do I do with the card? It still has to go back into the I don't know this pile. And then psychologically, I've had no progress after all this time studying. So one card, one question, one answer on the back. And all my answers, all my questions explain the science and the math behind it. I have imagery, I have pictures of charts, and a lot of the artwork I've done myself to explain the answer in detail like what you saw here. I am a true believer that, and I've always taught and instructed this way, that I teach not just what to do, but what are the whys behind it. What's the math? What's the reason why this is the way it is, and why we do what we do. And it helps. It's always helped me then to be better at memorizing and understanding those concepts if I understand the foundation, if I understand the whys behind the whats. And if you know me, you know I say that all the time. So if you've liked this, you would like my instrument study flashcards. You would also like my private pilot. This is more instrument related, but private pilot, you could use this too as well. And you can find both those cards at 777aviation.com. That's my push. There you have it, 777aviation.com. Reach out, man. I'd love to hear from you guys, and take care.